Quantum encryption is often described as unbreakable. The physics says attackers can't copy qubits, can't clone states, and can't hide their presence. But here's the truth. Real systems don't fail because of quantum mechanics. They fail because of hardware. In this video, you'll see exactly how hackers bypass BB84, blind detectors, hijack single photons, exploit timing windows, inject fake wavelengths, and force the system to give them the key, without triggering alarms. This isn't science fiction. These are the real attacks used in labs, research papers, and commercial QKD systems around the world. Let's break quantum encryption. To understand how quantum encryption is broken, you first have to separate the theory from the hardware. The theory behind BB84 is perfect. You can't clone a qubit. You can't measure it without creating errors, and the randomness is fundamental, not algorithmic. But real hardware is not perfect. Detectors drift, timing windows slip, photon sources leak multiple photons, and the classical channel is often wide open. So when attackers break quantum encryption, they don't violate physics. They exploit imperfections in the devices that implement the physics. Quantum theory guarantees security, but the hardware determines how secure you actually are. Here are the main real-world hardware weak points. First, detector blinding and control. This is where an attacker forces single photon detectors into a classical mode, so they ignore real photons and only react to the attacker's signals. Second, photon-number splitting. If the source accidentally emits multiple photons, Eve steals one copy and learns the key without adding detectable noise. Third, timing and afterpulsing exploits. By manipulating the detector's response window, an attacker can bias which detector fires and tilt the measurement outcome. And finally, Trojan-Horse attacks. Eve injects controlled light back into the device to read out internal settings and extract key information before the photons are even measured. These are the real-world weak points that allow attackers to break quantum encryption, not by defeating the physics, but by exploiting the hardware. Let's look at each one in detail. The detector blinding attack is one of the most effective real-world compromises of BB84 because it bypasses the quantum channel entirely and targets the hardware. First, Eve sends a bright classical laser pulse into the quantum channel, far stronger than any single photon. This overwhelms Bob's avalanche photodiode. Second, the APD becomes overloaded and drops out of its sensitive Geiger mode. Instead of detecting individual photons, it enters a completely blinded state. Third, once blinded, the detector behaves like a linear, classical photodiode. It no longer fires from true quantum events. The hardware is no longer operating in the regime that BB84 assumes. Fourth, because the APD is now in this linear mode, real single photons from Alice are ignored. The authentic quantum signal is effectively silenced. Fifth, Eve sends her own controlled classical pulses that cross the detector's threshold only when she chooses. This produces clean, noise-free clicks, keeping the QBER unchanged, so Alice and Bob never detect the intrusion. This attack proved a critical lesson in quantum security. Attackers don't need to break quantum mechanics. They only need to manipulate the devices that measure it. This graph is optional and is there for the real technologists and our viewers. It gets into great detail as to the technicalities of this attack. This graph shows how a single-photon avalanche photodiode, the detector used in most BB84 systems, responds as the incoming optical power increases. What we're looking at is not just theory. These curves reflect the same behavior demonstrated experimentally in the landmark detector blinding attacks performed by Makarov and colleagues. On the far left side of the graph, in the single-photon regime, the detector is operating in what's called Geiger mode. In Geiger mode, The APD is biased above its breakdown voltage. A single photon striking the semiconductor junction initiates an avalanche of carriers, producing a digital click. This is the regime BB84 depends on. Every photon is a quantum event. Every click is meaningful. This is the green dotted line labeled QKD single photon level. At these very low power levels, on the order of hundredths of a microwatt, the detector behaves exactly as the protocol assumes. It responds strongly to quantum states and ignores classical background. Now look toward the center of the graph. As the incident power increases, the APD begins receiving more photons per unit time. At first, nothing seems wrong. The detector still outputs full digital avalanches. But as we approach the yellow dashed line, the blinding threshold, the device begins to saturate. Once the optical power reaches this threshold, the APD can no longer fully recover between events. Its internal electric field collapses, and the device is pushed out of Geiger mode. This is the critical moment where BB84's security assumptions fall apart. Right at the blinding threshold, the detector has effectively stopped responding to single photons altogether. Its avalanche gain is suppressed, its bias point is altered, and instead of behaving like a quantum detector, it becomes a classical linear photodiode. This transition, from Geiger mode to linear mode, is the basis of the entire detector blinding attack. Once we move into the region to the right of the blinding threshold, the cyan quantum response curve collapses almost to zero. Here, Alice's legitimate single-photon pulses, arriving at QKD power levels, no longer trigger any measurable avalanches. The system has, in effect, become blind to quantum information. This is exactly what Eve wants. Now look at the red curve rising on the right. This represents Eve's classical control response. At these higher powers, hundreds of microwatts to milliwatts, the APD behaves like a linear photodiode. This means that Eve can send bright classical pulses that produce a proportional photocurrent, not a quantum avalanche. If Eve tunes the amplitude of her classical pulses, she can force the detector to fire only when she wants it to, and only in the basis Bob has selected. This is the red dotted line labeled Control Pulse Region. It marks the power levels where Eve gains full deterministic control. Here's the key insight. In this classical regime, the detector only clicks when Eve sends a pulse that crosses the threshold. She can make it fire in the rectilinear basis. She can make it fire in the diagonal basis. She can even choose which detector output, 0 or 1, will register as the correct measurement. And because all of these clicks are classical, not quantum, they introduce no additional QBER. This is why detector blinding attacks are so devastating. BB84's security relies on the idea that Eve cannot observe or manipulate photons without creating errors. But in a blinding attack, Eve never touches the qubits at all. She simply forces the detector out of the quantum regime and into a classical one where she can dictate the outcomes. To Alice and Bob, everything looks clean. The error rate is unchanged, the key length is normal, but the entire protocol has been compromised at the hardware level. This graph highlights one of the most important lessons in quantum cryptography. The security of a quantum protocol is only as strong as the classical devices that implement it. The physics is unbreakable, but the hardware is not. And when the detector is forcibly pushed into the classical regime, the entire quantum protocol collapses. In BB84, Alice does not send ideal single photons. In nearly all practical systems, she uses weak, coherent laser pulses, faint light bursts that on average contain less than 1 photon. But weak, coherent pulses follow Poisson statistics. Most pulses contain 0 or 1 photon, but some pulses carry 2, 3, or even more photons. And every time that happens, the door to a photon-number splitting attack opens. Here's how it works. When a multi-photon pulse leaves Alice, Eve inserts a beam splitter, a non-destructive optical tap, into the channel. She doesn't have to absorb or disturb anything. She simply splits one photon off and forwards the remaining photons to Bob. Because Bob still receives a valid quantum pulse, with the right basis, the right polarization, and enough remaining photons to trigger his detector, he never notices the intrusion. There is no additional noise, no timing changes, and most importantly, no increase in QBER. Eve now holds a perfect copy of Alice's qubit, safely stored in quantum memory. She doesn't measure it immediately. That would collapse the state. Instead, she waits. She lets the protocol continue normally. After Alice and Bob announce their measurement bases on the classical channel, Eve measures her stolen photon in the correct basis. At that moment, she learns the raw key bit with certainty. Exactly the same value Bob recorded. This is what makes the photon number splitting attack so powerful. Eve steals quantum information without disturbing the quantum channel. Bob's detections look normal. Alice's transmissions look normal. And because the error rate stays low, the protocol gives no indication that the key has been compromised. In short, when the source emits multi-photon pulses, Eve gains a perfect side channel into the quantum states, one that doesn't rely on blinding detectors, manipulating timing, or introducing errors. This attack fundamentally changed the design of practical QKD systems. It forced researchers to adopt countermeasures like decoy states, source monitoring, and strict photon number statistics to prevent Eve from siphoning off the key in secret. PNS doesn't attack the detectors. It attacks the source. It breaks the protocol by exploiting the statistical imperfections in the photons themselves. Photon number splitting attacks take advantage of the fact that most practical BB84 systems do not generate perfect single photons. Instead, Alice uses weak coherent pulses where the number of photons in each pulse follows a Poisson distribution. The probability of having exactly n photons in a pulse is given by the standard expression appearing on the left, where mu is the mean photon number. If mu is small, most pulses contain 0 or 1 photon, but a small fraction will contain 2 or more. The probability of generating a multi-photon pulse is roughly the expression on the right, which, for typical values like mu, equals 0.1 is about half of 1%. That may sound small, but in high-rate QKD systems transmitting millions of pulses, Eve gets thousands of exploitable events. Once Alice emits a multi-photon pulse, the physics allows something dangerous to happen. Eve inserts a passive beam splitter into the channel. Because two or more identical photons were created together, Eve can non-destructively siphon off exactly one photon from the pulse, sending the remaining photons forward to Bob. This is crucial. Bob receives a valid quantum signal with the correct polarization and timing, so from his perspective, nothing unusual has happened. The QBER does not increase. The arrival statistics look normal, and the protocol continues exactly as Alice and Bob expect. Meanwhile, Eve stores her stolen photon in quantum memory without measuring it. The stolen photon is still in the same quantum state that Alice prepared. Eve now waits for the classical reconciliation step, where Alice and Bob publicly announce the basis they used for each qubit. Once the basis is revealed, Eve measures her stored photon in the correct basis. Because her photon was an exact duplicate of the one Bob received, she learns the raw key bit with certainty. Bob records a valid bit, Alice records a valid bit, and Eve silently records the same bit. The protocol sees no disturbance. It has been compromised at the photon source level, not at the detector. This is the essence of the photon-number splitting attack. It bypasses all of the protections based on the no-cloning theorem. Because Eve isn't cloning anything. She is simply exploiting the fact that Alice unknowingly emitted two identical photons. It bypasses all the protections based on disturbance and QBER because Bob still receives a clean, undisturbed photon, and it bypasses any detector-side countermeasures because the attack happens before the detection stage. This vulnerability forced the development of decoy state, QKD, where Alice varies the mean photon number mu from pulse to pulse in order to detect Eve's splitting behavior. Without decoy states, a weak, coherent BB84 implementation is fundamentally insecure against an adversary with even modest optical hardware. In short, the photon number splitting attack is a source-side weakness that exposes the raw quantum states long before they reach Bob. Eve doesn't have to break quantum mechanics. She only has to exploit the unavoidable Poissonian statistics of weak, coherent light. This is why precise photon number control and decoy state techniques are essential for any real-world, secure implementation of BB84. The fourth attack we'll discuss is called the time shift attack. In this attack, Eve doesn't touch the quantum states themselves. Instead, she interferes with time. As Alice sends single photons down the fiber, Eve the eavesdropper inserts a precise delay or advance into each pulse. This timing shift changes the moment each photon reaches Bob's detectors. Why does this matter? Because Bob's detectors are never perfectly identical. Each one has a slightly different efficiency curve, a window of time where it's more likely to click, and a window where it's less responsive. By shifting the photon's arrival into one detector's strong zone and the other detector's weak zone, Eve biases which detector fires, without introducing the kind of errors that Alice and Bob normally rely on to detect eavesdropping. In the timing depiction, you can see the expected arrival waveform in blue. Eve's delayed and advanced pulses in the red area intentionally land in regions where the detectors respond unevenly. This subtle imbalance gives her partial information about the bit value, while keeping the quantum bit error rate deceptively low. The result is one of the most elegant attacks in quantum cryptography. No cloning, no intercept resend, no bright light blinding, just timing manipulation that quietly exploits detector imperfections. And unless Alice and Bob actively monitor arrival statistics at the nanosecond level, this attack can go completely unnoticed. In this graphic, we're looking at the inner mechanics of the time shift attack, one of the most subtle and devastating side-channel exploits ever demonstrated against real quantum key distribution systems. What you're seeing are the efficiency curves for Bob's two single-photon detectors, labeled here as Bob-D0 in cyan and Bob-D1 in red. These curves represent how sensitive each detector is depending on the exact arrival time of a photon. In a perfect system, both detectors would have identical efficiency across all times. But in real hardware, they don't. These mismatches, small, asymmetrical, and entirely unintentional, open a door for Eve. Let's understand the curves. The cyan curve, peaked on the left, is Bob's D0 detector. It is most efficient, meaning it is most likely to click when the photon arrives slightly earlier than expected. The red curve, peaked on the right, is Bob's D1 detector. It responds best to photons that arrive slightly later. The vertical white line in the center marks the expected arrival time of every photon Alice sends. In an ideal world, Alice's photons land exactly on that center line, giving each detector a fair chance to register the outcome. But that's only in the ideal world. Now, where does Eve exploit the system? Look at the blood-red shaded zone on the left side of the graph. This illustrates Eve's manipulation window, a region where she subtly advances the arrival time of each photon before it reaches Bob. By introducing just a few picoseconds of delay, or a few picoseconds of advance, Eve can force the photon to land inside the high-efficiency region of either D0 or D1. Here, in this shaded zone, Bob's D0 detector is operating at near maximum efficiency, while Bob's D1 detector is operating at almost zero. This is the heart of the attack. Eve doesn't change the photon. She only changes when it arrives. And that alone determines which detector fires. Now notice that this attack does not raise alarms. At the bottom, notice how the red curve is practically glued to zero efficiency in this advanced region. That means when Eve shifts the photon early, Bob will almost never observe a D1 click, even when Alice encoded a state that should have caused one. Yet, here's the terrifying part. Because Eve only shifts timing in a direction that favors one detector, the error rate stays low, and Bob assumes everything is normal. The QKD protocol, BB84 or otherwise, only checks for error rates. It does not check for detection efficiency bias. So Eve extracts the key without causing the usual disturbances that would reveal her presence. Here is a brief summary of the important technical points. This single graph captures the entire vulnerability: 2 real detectors with non-identical efficiency curves, a single Eve who can tune arrival times, a bias in detection outcomes without introducing quantum-level noise, a full key compromise with no alarms raised. This is why modern QKD systems now include countermeasures such as decoy timing, uniform gate shaping, and detection efficiency equalization. Because without these defenses, timing attacks like this give Eve an invisible, surgical tool to steer measurement outcomes without ever touching the quantum state itself. Our next attack is the Trojan-Horse attack, also called the wavelength injection attack. This is the method behind what you're seeing here: basis leakage. Eve secretly injects a faint probe beam back into Alice's quantum device, usually through the same fiber that carries her legitimate photons. When this hidden probe travels inside the device, it interacts with Alice's phase modulators. Those modulators unintentionally imprint their current settings, the actual basis choices, onto the returning light. This means Eve doesn't need to intercept any photons at all. She simply shines light in, and sensitive back reflections leak out the critical information she needs. What looks like an ordinary optical reflection actually encodes Alice's secret quantum settings. If Eve collects enough of these reflections, she can fully recover the basis sequence and dramatically reduce the security of the protocol. This is why modern QKD systems use optical isolators, power monitors, and wavelength filters to block any unauthorized light entering the device and to prevent this kind of covert basis leakage. Now let's break down what's actually happening under the hood during a Trojan-Horse attack. The chart you're looking at shows the reflected probe intensity as a function of Alice's modulator setting, and this is exactly where the basis leakage occurs. Here's how it works. When Eve injects a faint probe beam back into Alice's quantum device, that light passes through the same phase modulators Alice uses for BB84, even though none of Alice's legitimate photons are being intercepted. The probe beam still feels the current basis setting because the modulators impose a phase shift on anything passing through them, including Eve's injected light. The critical weakness is that part of this injected light gets reflected back out of the device, and that reflected power is not constant. It actually depends on the modulator's internal configuration, in other words, the basis Alice is using. In the graph, each bar represents one of Alice's 4 phase modulator settings: 0 degrees, 45 degrees, 90 degrees, and 135 degrees. And notice how each of those settings produces a different reflected intensity. This separation, these clear distinct peaks, is the basis leakage. The values on the graph, numbers like 0.62, 0.48, 0.71, and 0.55, represent the normalized reflected intensity of Eve's probe light. Normalized simply means we've scaled the measured optical power to a range between 0 and 1, where 1 would be the strongest possible reflection and 0 would be no reflection at all. So a value like 0.71 means the reflected probe returns with 71% of the maximum detectable intensity, while a value like 0.48 means only 48% returns. These differences matter because they correlate directly with Alice's basis setting. Higher or lower reflected power tells Eve which internal phase modulator state is active. As long as the reflected intensities are measurably different, like you see here, Eve can reliably distinguish the basis and extract secret information without disturbing the quantum channel. What this means is that Eve can take her returning probe light and measure its amplitude with a standard photodiode. She doesn't need quantum technology, she doesn't need entanglement, she doesn't need to intercept photons in flight. She just injects classical light, records the reflections, and uses those intensities to infer which basis Alice is applying at every clock cycle. Once Eve reconstructs Alice's basis sequence, the protocol is severely compromised. Eve can now tailor her eavesdropping strategy to match the exact preparation states, dramatically increasing her information gain while keeping the quantum bit error rate artificially low. This is why wavelength injection attacks are considered one of the most dangerous practical threats to early QKD systems. Modern systems defend against this using optical isolators, wavelength filters, and real-time power monitors that detect unauthorized inbound light. But without those countermeasures, a Trojan-Horse attack can silently extract basis information without disturbing the quantum channel at all. A perfect example of how quantum security depends not only on physics, but also on robust engineering. To finish up, let's summarize what we learned. The first vulnerability we looked at was detector blinding and control. Here, Eve overwhelms the avalanche photodiodes with strong classical light, forcing them to ignore real quantum photons and click only when she tells them to. Next, we explored the photon-number splitting attack, or PNS. Whenever Alice accidentally emits multi-photon pulses, Eve can peel off one photon for herself and forward the rest undisturbed, quietly learning key bits without raising the error rate. We then examined timing and afterpulsing exploits. By shifting photon arrival times or triggering afterpulses inside the detectors, Eve can bias which detector fires, effectively steering Alice's measurement outcomes. And finally, we looked at the Trojan-Horse or wavelength injection attack. A faint probe beam injected into the device picks up Alice's modulator settings, and the reflected intensity leaks the basis information Eve needs to compromise the protocol. Thanks so much for watching. If you found this video helpful, make sure to like the video and subscribe to the channel. It really helps us grow. For hands-on practice, visit specterai.ai and explore our full library of real-world quantum security labs. Learn by doing. You can also check out our books on Amazon for deeper study. We have the student and instructor manuals available for each of the 55 real-life labs. You'll learn about each of the 4 attacks in detail, and please leave a comment to tell us what you want to learn next. Thanks again for being part of the Specter AI community. We'll see you in the next video.